Yeah, in real code, it's not very common because spaghetti code, spaghetti go-tos have to be, in essence, yeah, I'm sorry about that, but once the idea got in my head, I just had to try it. Hello, Internet, and welcome to the Ground Up Coder. Welcome to the Ground Up Coder. Today we're going to be talking about irreducible control flow graphs. So originally, this was going to be the Stackifier video. In fact, I was just going to have one Stackifier video. But as I've been learning more and more, I've realized that we need both preparation videos and also the Stackifier video itself needs to be split up. Right? So why is this not the Stackifier video? Stackifier is easier to implement when you're working with a reducible control flow graph. Strictly speaking, there are variants of it which can handle irreducible control flow graphs while you're working on it, but for our purposes, when you know your control flow graph is reducible, it gives you more flexibility. Regardless of whether we do this before the Stackifier or within the Stackifier, we need to pick a strategy of how to handle irreducible control flow. If we were trying to translate a programming language where irreducible control flow was essentially impossible, this wouldn't be so much of an issue, but I want to support goto, switch, and Duff's device, and all that goody stuff. And that does require dealing with irreducible control flow graphs. So that begs the question, like, what exactly is irreducible control flow? So it's reducible if every loop has exactly one entrance. Let's look at a concrete example. So you have some code here that turns into this control flow graph. Now, if you follow the arrows, you'll actually see that these three blocks, they form a strongly connected component. So from the outside, the only way to get in actually is here, the while head block. So you can get from this block to this block to this block. And then this block unconditionally jumps back to this block. But this is kind of the classic demonstration of what you might see as a connected component. The thing that makes this one reducible is that there's only one way to get into this set of blocks from the outside. You can have multiple arrows coming into this block, but there can be only one block in which you enter from the outside. Intuitively, what reducible gives you is that you can pick one of the blocks to be kind of the starting point of your loop. If you have multiple places coming in, you kind of have to pick, okay, well, how do you start entering the loop? So let's look at an irreducible graph. So yeah, so like let's look at the actual loop in here as well, right? Just to clarify without looking at the control flow graph itself, let's first look at the source, right? This is essentially a do-while loop. So from the source side, irreducible control flow means that there's more than one entry into the loop. This forces you to have some sort of control flow that will jump into the middle. So let's see what that looks like in the actual control flow graph. You can actually see this loop here be reflected in these three nodes. The section starting label A is this block here. Section starting label B is this block here. If the condition is true, you branch into label B, which is this jump right here. If the statement was not true, then you jump into label A, which is up here. This loop has two different ways in which you can enter it. If you want to structure it with while loops, the while loop requires that you put something at the top. There's some point at which you enter the while loop naturally, top to bottom. But if you have two different entry points, you have to pick one. So if you have an irreducible control flow graph, how do you turn that into a reducible one? There are two general strategies. One is to clone some nodes, also called node splitting. And the second approach is to add a dispatcher node. Let me explain approach one first. So what does it mean to clone nodes? So the problem fundamentally is that you have these two blocks, say A and B, and there are two different paths into the block, right? This is kind of our fundamental tension here. You have a loop, and then there are two different ways you can enter it. The way that we solve it by cloning it is we pick one of these entry point nodes as the canonical one and say, okay, when you're entering this loop, you always enter through this one. And then how do you solve the cases that fall through the other one? Well, you make a clone of that block, and then it turns out you might need to make a clone of a few others as well. And this set of blocks, instead of looping it within itself, will redirect all the cases where you'll fall into A to block A. Essentially, you kind of need to clone enough of the graph so that it will bring you back to A. In a simple case, you might only need to clone B. And because A will never point back to B prime is not part of any loop. The tricky thing about this is that what do you do about the edges where B points into C? Because if you don't clone C, and if you just have B point into C, then you created the problem of having a second entry point again, right? So you actually need to clone C as well, and then have that map back into A. So the nice thing about this is that if you can do it, it gives you practically no runtime cost, except for the fact that your code bloats. In the worst case, you actually can have an exponential explosion in the number of nodes. So there's a bit of a simpler approach if you're willing to pay a little bit of a runtime cost. And the idea is to have, just instead of having cloning a multiple collection of nodes, you actually create only one extra node that serves as the entry point into the loop and dispatches back into all of the blocks that used to be the entry points. So what does this cost us? Well, you need one extra variable. Whenever you jump into one of the entry points, any place you used to jump into the entry points, you actually need to update a single variable that indicates which one you want, and then you jump into the dispatcher, and the dispatcher will look at that local variable and pick out which block to jump into. So what does that look like in the graph? So here's our previously irreducible graph. Here we had this loop here. We had two different entry points, label A and label B. Once we do the transformation, you'll see that we only have one extra node here. Everything else essentially looks the same, right? Everything before the loop, everything after, inside and after the loop looks very similar, except that you have this one extra block that we just created. This is the solution I ended up going with for this one. So in a real production compiler, they actually they use both. If the cost of node splitting is cheap enough, that's what they'll do. If the cost of node splitting looks like it's going to explode, then you'll go with the dispatcher approach. For now, I've decided to just go with the dispatcher approach and then come back and add node splitting if it turns out that's something that would significantly improve the performance. And even with the dispatcher approach, there's some subtleties here. There are actually two different sets of edges that come into the entry points. One are the ones that edges that come from outside the loop or the strongly connected component. Every edge that comes from the outside has to come into this block, right? So here you see the then end if, right? But then there's a question like, well, okay, like the whole point of this is to funnel all the outside edges into the loop. Why not have all the other guys still keep the loop, right? Because if you jump into the dispatcher block, you pay a price. Like you have to pass in dummy variables, dummy values for the branch that you don't use, and you have to do a switch on which block to enter, which is, you have to determine at runtime which one you're entering. That's going to cost something, right? But you can see that like you have to have at least one edge up here, right? The whole point is that you want to have a strongly connected component with only one entry point. Well, if you don't make this block a part of the strongly connected component, then you're coming back to the same problem. All the old entry points are still the entry points, right? So you need to have some of the edges be part of it. However, it turns out you don't need to have every edge go into it, right? So like there are some cases where you can avoid paying that extra price by not having some of the edges go back in. It turns out for some of the internal edges, you can avoid them. There's also, even with the dispatcher approach, there's an optimization we can do where we can pick out which edges actually do have to be routed through and which edges don't. But it turns out to actually optimally figure that out turns out to be an NP hard problem. So even in production compilers, you only do back edges, even if that's not the optimal set. Okay, so what does this actually look like in code? The top level set of code actually is pretty straightforward to follow. Tarjan, this is a standard algorithm for finding the strongly connected components. You loop through the strongly connected components to find one that might be irreducible. If the size is length 1, a single block strongly connected component can't be irreducible anyway. A single block is always reducible, so we skip those. But if we find one, turn out to have more than one entries, and entry is pretty straightforward to check as well. You look through all of the blocks, you check the predecessors of the blocks, and then see if the predecessors are included or not. If a block has a predecessor that is not included inside the strongly connected component itself, then that block is an entry, right? So you can list all the entries in a fairly simple way. If you have more than one entry point, then that's irreducible. You have to do something about it, right? And then the thing you do is we insert the dispatcher there. And then we also have to, we have to make sure that we get all of them. Part of the tricky thing is that like, if you create a new block that changes the shape of the graph, fixing one irreducible SCC might reveal another SCC that is irreducible that you have to fix. There are some smarter ways to do this. In this case, I just wanted to keep things simple. We just go back and just make sure that as long as we see any irreducible components, we keep on repeating until we get rid of them. So the hidden complexity here in this nice looking set of lines that fit in one slide is this one here. And it's not hard code per se, like so inserting that dispatcher node, the actual code where you create the block itself, and then at the very end you do something like this where like you need to take a snapshot of the previous entries and then you need to redirect their edges. So conceptually it's not hard per se, it's just a little bit messy and you need to kind of do it carefully. Right, so what is the result? I guess is going back to the previous slide. The whole process essentially boils down to, okay, you detect an irreducible graph, you add an extra block here, then make this block the sole way to get into the nodes that used to be the entries, and then now your graph is reducible. Okay, so when will we see the stackifier? Before, I kind of said that this video was going to be the stackifier video, but as I'm learning more, as I'm studying the stackifier more and more, I'm coming to realize there are just a lot of different pieces that you have to put together. It would be useful to have one video that conceptually explains what it is and what we're trying to achieve, and then there's the tricky part of ordering the blocks, which I think deserves its own video. And then also, something I kind of missed doing earlier, which I think would have been useful, because this is not a standard C feature, but many other languages have it, which I think will be nice to use when describing what the source looks like, is a concept of labeled while loops. Right, so like if you've seen like Java code, JavaScript has this too, I think. When you have like nested while loops and sometimes you want to break outside the outer loop, that feature turns out to be very useful in order to describe what it looks like, because that's essentially the WebAssembly looping primitives allow you to do. I don't know if the labeled while loops are going to be a separate video, probably not, but I think it does need to be covered at some point in one of the videos as well. So yeah, I hope that's better. We'll see. We'll see how it goes. Yep. Until next time.